Hello friends, welcome to Ansys-Tutor. In this video, we are going to see the flow over a double wedge supersonic aerofoil. We are going to analyze this in ANSYS Fluent CFD solver. So let's start. First of all, we are going to start the ANSYS Fluid Flow Fluent. Right click on geometry, go to properties and select analysis type as 2D. Now right click on geometry and select new design modeler geometry. Go to units tab and select units as meter. Select the XY plane. Click on the Z axis. Go to sketch, draw a rectangle. Then go to constraints and select symmetry. Select the axis first, then select the two lines of the rectangle. Put the dimensions. We are going to create the wedge shape first. Use the move tool to move the dimension nearest to the sketch so that it would be better to visible. Now click on generate. Go to draw panel. Draw a polyline starting from the middle of this rectangle, then the sidewise. Now go to constraints. Use the coincidence option to merge the two lines into single point. Then select the midpoint constants. Select the line of the rectangle first, then the vertex point of this rectangle, so that it would be coincidence. Now click on generate. Now go to modify tool and remove out the unnecessary lines. Here is a point remaining, so we are going to remove this using the point tool. Go to select option and select it as point selection tool. Select this point and click on delete. It will be deleted. Now we are going to draw a outer fluid domain around this aerofoil. Draw a larger rectangle. Put the symmetry constants. Now put the dimensions. Now click on generate. Go to concept menu and select surface from sketches. Click on this sketch and then click on apply. Select the operation as add frozen and then click on generate. This is our fluid domain which is around this wedge shaped aerofoil. The geometry is complete. We can now proceed for meshing. Right click on mesh, select edit. The meshing workbench window will open. Right click on the mesh and select sizing option. Select the edges of this fluid domain, outer fluid domain. Hold the control key to select all these four sides. Then click on apply. Enter the element size as 1 meter. Then insert another sizing for the sides of this aerofoil. Select all the four sides. Then click on apply. Enter the element size as 0.01 meter. Then insert the meshing method. Select the fluid domain and select the triangular methods. Go to default mesh setting. Go to sizing. We are going to change the growth rate to 1.07. Then the defeaturing size. Mesh defeaturing, we are disabling the mesh defeaturing. Capture curvature option as no. Capture proximity as yes. Then now we are going to generate this mesh. The mesh is currently generated. You can see there is smaller cells around this wedge, aerofoil wedge, and gradually larger cells towards outer surfaces. Now we are going to name these boundary surfaces. Select all the four sides and name it as wall swing. Click on OK. Select this outer walls and name it as pressure far field. Now we are going to update this mesh. You can see that mesh is now updated. This mesh is linked with the Fluent solver. Close this meshing and we are going to open this Fluent solver. Select the double precision option. Then click on start. This is the Fluent setup window. I have selected the dark theme, so it is black in color. So start with the analysis. We are going to turn on the energy equation. Then select the fluid flow model as inviscid. Go to General tab and select it as a density based solver type. Then go to Materials, go to Fluid, select Air, change the density of the air, change the density to ideal gas, keep the default value of specific heat and molecular weight of air, then click on Change Create. Now go to Boundary Conditions, select the pressure far field. You can see that according to the names, the Fluent already assigned the boundary surface type as pressure far field. Click on Edit. Gauge pressure as 101,325 Pascal. Mach number as 3. Give the default temperature of the air, then click on Apply. Click on Close. Now go to Operating Conditions and make the operating pressure as 0. Then click on OK. Now in the reference value you can see the reference value we can see the pressure as 0. So while we are selecting compute from inlet or compute from far field, it would show the assigned pressure at that point, at that location. Now we have selected pressure far field. Now you can see pressure is 101,325. Now go to Solution Methods. Select Formulation as implicit. Select Gradient as green gas cell waste gradient. Keep the flow as second order upwind. Now go to Controls. Go to Monitors. Select the residuals. Decrease the continuity residuals up to 10 to the power minus 16 so that the solution would be more accurate. Now go to Initialization tab. Select the standard initialization. Select compute from pressure far field. Then click on initialize. Now we are going to save this case file. Select the location where you want to save this case file. Name the case file and click on OK. the case file will be saved in the desired location. So if you are losing something or you want to change something, you can access that case file later. You do not require to be set up all these things again. You can just import that case file so that it will be loaded from that position. Now run this calculation. Calculation is complete. Now we are going to analyze these results. Go to contours. Contours of velocity and Mach number. Click on save or display. Here is the Mach number contour. Go to color map options. Enter the color map size as 20. Click on apply. Set it as RGB color. Now go to color map editor. Select it as RGB color. It's red, green and blue. Then click on apply. This is the default Fluent color map options. This is red, blue and green. Now we are going to save this image. Select the image resolution. Enter the path of the location. Enter the path where you want to save this file. Enter the location of the file where you want to save. Save this contour image file. Now we are going to refine this mesh. For that we are going to use the adapt method. Adapt, then select the region. Click on manual mesh adaptation. Go to cell registers. Select new. Select the field variable. The field variable option. Select the type as top value cells. Derivative option as gradient. Select gradient as velocity. Gradient of Mach number. Change the HD value to 90%. Cells having value upper than 90%. You want to save this one. Select the gradient and click on adapt. Then click on close. Now run this. After saving the sketch file, we are going to run this calculation again for 400 iterations with a refined mesh. Then click on calculate. Calculation is complete. We are going to analyze second contour, which is a refined mesh than the previous one. and save this image, contour image. Also export this case file with another case name. Then click on OK. Close the Fluent solver setup and proceed for CFD post processing. Insert a new contour in this CFD post processing. Select the location as symmetry 1. Select the variables as velocity. Then click on apply. This is your velocity contour. Just turn off this wireframe so that it will be properly visible. Now we are going to add a streamline which would start from pressure far field and click on apply. Enter the number of points as 1000. Save this contour image in white background so that it would be easier for the presentations. Check the pressure contour. With this, let's conclude this demonstration. If you have any query or doubts, please comment, like, share and subscribe to our channel. Thank you. Keep learning, keep exploring.